All right, thanks for inviting me to give a talk today. This is going to be a great segue from Dave's talk, talking about how we move further into the infrared, what can we learn on the lunar surface. So I'm going to be talking today about looking at essentially what I call volatile contamination. Maybe that's not the right word for it, but really we're looking at using a new technique or a series of new techniques that I call active illumination spectrometers to understand how the volatiles that come out of these landing plumes impact the surface, spread across the surface, both in kind of the local and the further extent regimes, and how we've got two new instruments in development here at Goddard to help do that. Next slide, please. So this has been talked about a lot already, so I'll skip through most of the background aspects, but the important part here is that the landers of any size, particularly the large HLS class landers, will, put out an enormous amount of particularly water and CO2 onto the surface surrounding the nominal landing site, up to tens of kilometers away, depending on both the lander and also its trajectory. And those volatiles are going to fall on a number of different surfaces, thermally and illumination-wise. So just based on the physics, the local time-dependent shadowing and things like micro cold trapping are going to have a huge effect on the where volatiles are placed on the surface and where they stick around on kind of the short time scale. So here we're talking about kind of hours to days, and what can we learn in those time periods about things like volatile distributions both before the landing occurs, immediately after those events, and then how do these kind of active experiments that are ongoing change the distribution of volatiles in the short term kind of hours, days, and weeks following these landings or ascents, and how can we use that to both learn about the dynamics of volatiles, how they move across the surface, but also where these volatiles might end up, and going to the contamination point, might these contaminate natural volatile reservoirs that are near the landing sites for these missions. Next slide, please. Okay, so this is just an example of kind of what we're talking about here when we talk about short time scales and volatile emplacement. So this is just essentially looking at a 100 nanometer layer of both water and CO2. How long will that stick around on the surface for various surface temperatures? And you can see in the plot in the upper right there, we are looking at temperatures. Water sticks around on this kind of hourly, daily time scale up to temperatures of about 150 Kelvin. CO2, we think about it as kind of a super volatile that's only in the very coldest places on the lunar surface, which is certainly true on geologic timescales. But again, looking at the period of time right after these landings, on the hour to daily time scales, it can be potentially stable up to, 70, 80 Kelvin. And so the map on the left there is just looking at the Diviner summer average temperature up to 76 Kelvin, which is where our model said that CO2 should be stable on kind of the 1 day time scale. And you can see there's a lot of regions here that are, nominally pretty close to these Artemis landing sites, within kind of the 10 to 20 kilometers range. So there's certainly places where we might expect to see surface deposits of CO2 for potentially, hours or days in relative proximity to these landing sites. So the CO2, despite being a very unstable volatile compared to water, might be sensible on the surface near these landing sites. Next slide, please. Okay, so what's our method to kind of solve this this question about can we see these volatile emplacement and movement experiments in real time? So our approach is to use what we call active illumination spectroscopy, and the goal here is we bring our own light source with us, and we use that to determine the volatile abundance on the surface, regardless of lighting or thermal conditions. So that has a big benefit here. We don't need to rely on the local lighting conditions at the landing time. We aren't concerned with the specific topography with respect to lighting and shadowing. We aren't worried about needing to know the temperature of the surface very precisely to be able to understand thermal emission near this 3 micron band. We can remove the thermal component by looking in between laser pulses. And so that gives us a huge advantage over relying on the sun or just thermal emission for our light source in the spectrometer. And so we can do this using lasers, which allows us to expand into remote sensing, so we can cover large areas of the surface, not just limited to really close measurements. The molecules of interest for these landing plumes, particularly water and CO2 here, have vibrational features in the near and mid-infrared that we can cover with our techniques. And again, I mentioned we can use pulsed laser sources, and again, that gives us both measurements of reflectance, and we can do surface spectroscopy, but we can also do backscattering measurements to understand plume dynamics from the dust that's kicked up during these active events. And so the two instruments that are being worked on right now, first is called Spiral, which stands for Spectroscopic Infrared Reflectance LiDAR, and that's a funded DALI project that began about a year ago. That's currently a TRL4, and then there's also we call Tinsel, Tunable Infrared Spectroscopic Imaging LiDAR, and that's an early stage Picasso project, again, started about a year ago now, and that's at TRL2. Next slide, please. So Spiral is a orbital class LiDAR that measures at 6 discrete wavelengths. So you can think about this as kind of a multi-band reflectance experiment. And we're measuring both surface reflectance and topography. You can see the wavelength bands in the lower left there. So we have 3 wavelength bands, or I shouldn't say bands, 3 wavelengths in the 3 micron region to measure the band depth and shape of the all-important 3 micron water absorption band, or I should say OH absorption band. And then we have 3 wavelengths in kind of the near infrared from 1.6 to 1.8 microns or so. And those are used both to constrain the lunar background, but also understand things like optical maturity of the surface. There's also additional opportunity to potentially include a laser at 2 microns to measure the CO2 absorption feature there, but we're still working on that, how we can work that into the overall instrument, because that wasn't in the initial baseline plan. And again, the goal here would be we put an instrument like this in a polar orbit, and we use some cross-track pointing to take swath measurements across the landing site. And that would be on something kind of like a 2-hour orbit interval, similar to LRO. So we're measuring, a very limited swath in terms of width. Our beam is only about 40 meters wide, but we measure at a high rate, 100 hertz or so. And so we have contiguous coverage of the surface. And so we can use this cross-track pointing to kind of move our laser swath right across the landing site, and again do these measurements that are independent of lighting. Next slide, please. Tinsel, although from a science perspective we're making similar measurements, the instrument itself is quite a bit different. So here what we're doing is, you can think about this as kind of a multi-band imager. It's actually kind of a hyperspectral measurement, but it's a camera, a 3D camera, so it means that for each pixel in the camera, we also get a range, and we're using a laser illuminator here, a tunable, continuously tunable laser illuminator to take hyperspectral images of the surface. And so we're doing these measurements. These images come in series as we tune our laser across the wavelengths of interest. Here we've chosen 1.5 to 3.5 microns for our wavelength range. Again, that covers really key absorption features for both CO2 and water and OH. Similarly to Spiral, we're doing 0-phase reflectance measurements, so we don't have to be concerned about thermal emission or local lighting, because we can remove the kind of continuous source background in between our laser pulses. And we have both a low TRL version of the camera, that's a 16 by 16 pixel version, and then for the next round we're going to move up to a 256 by 256 version of the camera. And we're targeting kind of a rover mounted, ideally rover mounted system, but we're also looking at tripod mounted as well. Next slide, please. All right, so I'm running out of time, but here I just wanted to say that one real key of this monochromatic illumination technique that we're using is we don't really heat the surface at all because the flux density is very low compared to something like a supercontinuum source or a tungsten filament. Next slide, please. All right, these are just a couple CONOPS we're looking at, either looking at the area below the plume, doing backscatter measurements with tinsel, or looking at the surface around the landing site with an orbital LiDAR like Spiral. Next slide, please. All right, so I won't go over this, but I did have one question that kind of came out of this, which is, can we use techniques like this and CO2, which may be resident on the surface for short times, to act as a tracer for volatile migration and potential contamination following these landing events? Thanks.